So let's talk about number 8, okay, which I'm guessing is a question that everybody's going to have. So here's the setup. So here's the river gorge, okay, and then you got the river down here, right, and here's the bridge. So you're standing up here. So what's going to happen is I have rubber bands just for this to show you. Today is sucked, by the way, okay? I'm just telling you all now. Today is sucked. Okay, so imagine this is the bungee cord. It really isn't, but just go with it. Okay, so here's the setup. So you're standing up here on the bridge like this, okay? So you got this visual. So you're going to fall off the bridge, and you're going to be in free fall for a while until you begin to stretch the cords, okay? So that's what you're finding first. So on 8, you're told that, hey, you're going to be in free fall for 12 meters. So you're just going to use that equation, and you're going to figure out how fast you're moving at the end of that 12 meters. So at this point, the bungee cord is going to begin to stretch. So at that point, the only force acting on you was gravity. Okay, that's it. That's the only force acting on you is gravity. But once that bungee cord then begins to stretch, okay, like this, then you're going to have some upward force created by the bungee cord, okay? So that's going to begin to kick in. Now, the bungee cord is like a spring, and the spring, that force is going to equal kx. So once that bungee cord begins to get engaged, the farther you stretch that cord, the more upward force is going to be exerted on you. So the whole key to this is going to be on B, okay? So here's the setup on how you're going to do B, because you got to find the value of K. So at the end, this thing gets stretched another 19 meters, which gives you a grand total of 31 meters below the ground, okay? So here's the easiest way to think through this problem, is that reverse it and say, okay, let's say you were 31 meters below the bridge, and you're going to get lifted up 31 meters. So if you're here, and you get lifted up 31 meters, that's going to tell you how much UG that you're going to have, which is going to be mgh, okay? Because if you were just down here and you reversed the process and you got lifted up there, that's how much potential energy you would have in the system. Now, that has to equal the amount of us that you store when that spring is fully compressed. Okay, when that thing gets fully stretched out here, that's going to equal that value of your UG, because those two energies then are going to be equal. So that's going to equal, so my UG is going to equal my us, which is going to be 1/2 kx squared. Now, here's the trick. You've got the mass, you know G, this H is going to be the 31 meters, because that's the total value in terms of the exchange of this energy, okay? Now, on your K value, which is going to be 1/2 kx squared, this X is how far the bungee cord gets stretched, which in this case is going to be 19 meters. So, you know the M, the G, the H, you know this is 19. The only thing you don't know is K. So this is what's going to allow you to calculate the spring constant, okay? So, if all goes well, that answer on, your answer to A should be around 15 meters per second. And your answer to B should be around 100 newtons per meter. Okay? Are we good with that? Everybody cool with what I've done? Now, we get to see, that's what we just talked about. So when that bungee cord begins to stretch, you still have gravity pulling down and you have the bungee cord pulling up. Okay? So now, here's the thing. As you fall, the gravitational force is going to remain constant because that's just going to be mg. But as you stretch that cord, the force from the bungee cord is going to get bigger because of the fact that it's a linear function. So the farther you stretch that bungee cord, the more force upward that you're going to feel. So when you get to D, all I'm asking you on D is, hey, write a net force equation. So all you have to say is, wow, I've got gravity pulling down. I've got the force from the bungee cord acting up. Now, here's the deal, okay? Think this through. If you bungee jump and you want to stop, right? At some point, the force from the bungee cord has to be bigger than the force of gravity. Because if this bungee cord force is always less than the force of gravity, you're always going to be accelerating downwards. The only way that you can stop this train wreck is if this bungee cord force becomes bigger than the gravitational force pulling you down. Okay? So what you should see is that on that one, your net force, the force from the bungee cord has to be bigger at the bottom. That's what's going to make you stop. So this is just going to be, that net force is just going to be force from the bungee cord minus Fg. Okay? That's it. That's all you have to write. Now, on E, this is where you're going to have to do a little bit of thinking. Your net force is mass times your acceleration. This acceleration is what you're ultimately searching for, is this value right here, is this acceleration. Okay? Now, the force in the bungee cord, because it's following Hooke's law, is going to be Kx. Okay? You know the spring constant. You already found that. That's around 100. You know how far you've stretched the bungee cord. Oh, that's 19 meters. So you know these two values. You can calculate weight. Oh, okay, that's just mg. So, you know K, you know 19 meters, you know the mass, you know g, you know this mass, solve for that acceleration. So if all goes well on E, it should be something around the legal drinking age. If all goes well. All right. What else do you want me to go over on the assignment? Just type it in the chat box. Nine. Okay. That seems to be the general consensus. Okay. Now, everybody, number 9. All right. So let's talk about number 9. All right. There's a couple of different ways that you can work number 9. Okay. And I don't care how you do this. Okay. I'm going to show you the different options. So you're on top of a cliff, right? Okay. And you're going to shoot this thing out like this, right? So here's one way that you can do this problem. And if you like this, that's fine. Knock yourself out. So you can find your Vx, and you can find your Vy. And knowing Vy, you can go old school, and you can find this distance up to here, right? Just like you've done before, like that bridge, like that ball off the bridge problem. You know, Vy, your final velocity is going to be 0. Then you can find your maximum height, okay? then knowing your maximum height, then you can find your final velocity when you get down here in terms of a vertical velocity. So you can find this vertical velocity here when it lands, okay? Because you're going to know how high it is when it starts to fall, and then you can figure out how fast it's going vertically when it lands. Okay, that's an option. But when it lands, it also has a horizontal component to it, right? It also has a Vx, because it's going to have that same horizontal component that it has here. So then you can go, oh, it's going to land with some Vx, it's going to land with some Vy, and then you can find the resultant. So you're going to find Vx, your final Vy, take the square root of both of those, or square both of those, add them together, do the Pythagorean theorem, and get that resultant. That's one way you can do the problem. So if you like components and old school, fine, knock yourself out, it works. Okay? That's option number one. Now, option number two. Gannon Bird, when that ball is on top of that cliff, what's the two types of energies that it has?
It has kinetic, it has only potential when it's on that cliff.
Okay, when it's on the cliff, it just has potential, right? But then I'm going to throw it, right? Okay, I'm going to throw it. So then what else does it have?
Kinetic.
Kinetic. Now, Gannon Bird, when I calculate that kinetic energy, do I need that angle?
No.
Look, this is how you calculate kinetic energy. Is there any way on God's green earth I can plug the angle into this equation?
No.
No, it's not there. So here's what's going to be important. I'm on top of this cliff. If I throw that ball up, it's going to have a certain velocity and a certain kinetic energy. If I throw the ball down, it's going to have the exact same amount of kinetic energy. If I throw it at an angle like that, it's going to have a certain amount of kinetic energy. So this amount of kinetic energy does not change depending upon which direction I throw it. It's just going to be a certain amount of kinetic energy. So, when it lands, Gannon Bird, what's the only type of energy that it's going to have?
It's only going to have potential.
No. It's going to land.
Only going to have kinetic.
So they're going to have kinetic energy. So Gannon Bird, when I add the potential energy here and the kinetic energy here, what does that have to add up to?
What you get at the very bottom.
Oh, that's kind of cool. So that's going to be mgh plus 1/2 m v naught squared equals 1/2 m v squared. So, why didn't I give you the mass of the ball?
Because it doesn't matter.
Doesn't matter.
Cancel it out.
Yeah, I'm going to lose all the masses. Okay, those all go away. Oh, look, this is kind of cool. If I multiply it by 2, I get 2gh plus v naught squared equals v squared. I can just use that equation. Okay? Literally, that's all you have to do. But here's the reason that I put that problem in is that I want you to think of these problems in terms of energy. Oh, I've got UG and I've got kinetic. And here's what's important. I cannot emphasize this enough. This is a scalar quantity. The direction that I throw that ball doesn't matter. Okay, it doesn't matter. Up, down, left, right, sideways, nothing. Now, if I just drop the ball, this goes away, and my potential energy at the top equals my kinetic energy at the bottom. Okay, if I just drop the ball, that's all, it would just go away. Okay, and then those two values would be equal. But because I throw the ball, then I have an additional amount of kinetic energy, which is going to make this velocity bigger if I throw it than if I just drop it. Because if I just drop it, I only have UG. But if I throw it when it lands, then it has more energy to start with, which means it's going to have more energy when it lands. Okay, so everybody was cool with number 9. All right. Diego, you would find a way, I have no doubt. Okay. So let me make sure I got everything here. I think that's it. Okay, so let me give you some hints on some of these other ones. Because if number 6 is wrong, kind of everything else is going to be wrong. So on number 6, this is when you had that box and it was sliding and it was going to compress the spring. So it's like this cart rolling along and hitting, okay? Hitting the spring and compressing it. So your answer to number 6A should be a little bit less than 2 joules. Because if that answer is wrong, everything else is going to be wrong, okay? So your answer to 6A is a little bit less than 2 joules. And the same thing is true of 7 because that kind of builds off of each other. So your answer to number 7 for that velocity should be around 3 meters per second. Okay? Because if that's wrong, everything's going to be wrong. Now, especially on number 6 and number 7. So here's, you listen to me. Especially on 6 and 7. If you don't want to draw a chart and show me, oh, here's all my energies and here's how they add up, that's fine. But so help me, you mark my words. If you don't draw that chart and you have one answer that's wrong, I stop grading at that point and everything's going to be wrong from there on out. Okay? So, you all are big people. You can make that decision. Okay? But, and if your answers are right, hey, that's fine. Then you're golden. But if your answers are wrong and I cannot track what you did, I'm done. I'm cashing out my chips. Screw it. Not going to waste my time. Anyway, so anything else on the assignment for the good of the cause? Going once.
Over 4C.
On the stuff that I typed up?
Yes.
Okay, well, let's start at the beginning. Okay, your answer to 4A, because if that's wrong, everything is going to be wrong. Your answer to 4A is around 20 newtons per meter. Okay, because if your spring constant is wrong, everything else is going to be wrong. Okay? So what's happening on 4C is that you want to figure out how far it's going to stretch, right? Well, you have F equals Kx. So you know your spring constant value. This is just like a linear function. So you know your spring constant value, right? You know the mass. So you know the mass, so you can figure out how much force there is. Then it's just a matter of solving for x. So your answer to 4C should be around 0.3. Okay? That's an ish, but it should be something around 0.3. So Bodie, did that make sense? Okay. And your answer to number 9 should be around 200 meters per second, by the way. Okay, if we're good, anybody else? Going once, going twice? Sold. Okay. So that's good. All right, so I'm going to shift the cameras over here. And I sent you all out that lab. So it would behoove you to pull up that lab so you can kind of see what's going to be going on as I go through this. So give me a second to get these cameras shifted over here. hold on. How do I want to do this? Okay. Now I gotta get this. Okay, now, I realized that there's supposed to be a diagram on that bottom of that front page, but I realized I just sent you guys the Word document and not like the scanned PDF document that has this diagram at the bottom. So I'm gonna send you, the only thing that's gonna change is the front page, okay? So I'm just gonna send you the front page so that you know what X1 and X2 is, and that'll make more sense, okay? So I'm going to send you this so you have this diagram. I'm still going to explain the lab, but I just realized that when I looked at what I sent you all, because today's just been a train wreck from the beginning, that I forgot this diagram. But I'm going to send that to you right away. I'm still going to explain it, but it'll make more sense. So here's the deal. The first thing that you got to do on this lab, or that I'm going to give you the data for, is that you have to find the spring constant. So what this data is that we had this spring, and the position of these rings is going to be vital. So this ring, when I move this up, okay, so when you look at it, the bottom of this ring right here is completely level with the bottom of the spring, okay? So what I did to give you this data, hold on, let me get the other sheet, hold on. So on this data, and keep in mind that we're keeping track of elongation. So I've sent you all this column. So what I did is I said, okay, I took 0.4 kilograms. So 0.4 kilograms, and wouldn't you know it, the one mass I don't have, I need, hold on. So what I did is I took 400 grams, hooked them together like this, and then I measured how far this stretched from the bottom of this ring down to this point, okay? So I measured that, and that was 0.050 centimeters, that's that distance right here, which is 5 centimeters, okay? So I put 400 grams here, it stretched at 5 centimeters, which is 0.05. So then I went to, the next mass was like 500, so then I put on a 500 gram mass, boom. Then I measured how far that stretched, which was 0.065, okay? And then all I did is I just kept adding the masses until I finally got all the way down to the point that I had 1.5, which is this big massive one like this. Hold on. So now I'm here at 1.5. So that was the biggest force that I've got. And I stretched this out, and I measured how far it stretched, which is at 18.3 centimeters. So this last elongation, that 0.183, that's going to be vital later on. So at this point, if you all were in the lab, here's what I tell you to do, is draw a graph, and here's what's going to be important. When you draw this graph, you have to put force on the y-axis and elongation on the x-axis. So that's the first thing that you have to do in terms of this data analysis. You want to find the value of k. You want to draw that. This is the only graph that you have to draw. And you're going to do a lot with this graph. So you want to draw this graph as big as you can, okay? and then make this as neat as you can. You want to spread this out as far as you can with your force here and your elongation here, okay? Draw the points, and then you want to draw a line of best fit, okay? I can't emphasize this enough. You have to take a ruler, start at 0, 0, and draw that line of best fit, okay? Your data points are going to be pretty close together, but they're not going to be exactly linear, okay? So, that's the first set of data that you would collect. Now, the second set of data that you're going to collect is over here on page 2, okay? So this is where you have to have what I'm going to call x1, x2 in height. So, and again, this will make more sense once I send you this diagram, and I apologize for that. So, what you're going to do is you're going to make these springs oscillate. So what you're going to do is that I took 1.2 kilograms. So if you flip over and look at page 2, okay, page 2 is fine. You're not going to have to redo anything on page 2. Page 2 is golden. So what I did is I took 1.2 kilograms, okay, like so, and I hooked them up like this, okay, and I'm actually change this. I'm going to run out of room. Give me 1 second. That way I'm going to have more room to actually oscillate. That hook is bad. It rains, it pours. Okay. Okay. So, and we're actually going to do this lab a third time when we get into harmonic motion. So, what I did is that I'm going to make this oscillate like this, right? So, what you'll see, and this will make sense once I actually send you this diagram. So, I made this thing oscillate back and forth. So, what I did is I put, so this is where the spring was in equilibrium. This is at the top of the oscillation, and this is at the bottom of the oscillation. So, what this distance from here to here is what I'm calling x1. So here's how I want you to think about this. So over here on page 2, okay, this page right here, where I've got x1. So what x1 is measured from is from this ring down to here. So here's what I want you to think of, is that this distance from here to here is, leave the oscillation out of this whole thing. If I stretch this spring from this point down to here, I'm going to store a certain amount of energy. Okay, so leave everything else out of this. If I stretch this spring from here down to here, I can use 1/2 kx squared, and I can calculate how much energy that I store right here. So this is going to be x1 from here to here. So when this spring gets stretched to this point, this is how much energy that I'm going to store, 1/2 kx squared. So right here, down below on trial number 1, where it says us at x1. So what you're going to do on trial 1, us at x1, you can take 1/2 times your spring constant, which you're going to find off of your graph, and then you're going to multiply that by 0.1 squared. So this is going to be 1/2 kx squared. So you're going to take 1/2 times your spring constant times 0.1, and that's going to tell me how much energy that I'm going to store in the spring at that point right there. Now, then I'm going to do how much energy I store at x2. x2 is down here at the bottom of the oscillation. So when this thing is oscillating, so I've got x1, which is here. This is how much energy I store to stretch it to this distance. x2 is how much energy I store when I stretch it all the way down to here. Okay? So this is my x1 energy. This is going to be my x2 energy. So what the whole key to this lab is that you understand that we are doing nothing but exchanging different types of energy. So when this thing is oscillating, my amount of energy stored in the spring is continuously changing because my x value is continuously changing. So I've got a minimum amount of energy stored in the spring at the top. I've got my maximum amount of energy stored at the bottom of the oscillation. So I'm changing my value of us because I'm changing my value of x. Okay? Now, there's also gravitational potential energy. There's UG. So H is going to be the difference between x2 and x1. So here's the simplified way to think about this. Leave the spring out of it. If I just take 1.2 kilograms and I lift it from this point here, right here, up to this point right there, that's going to be a change in my gravitational potential energy, which is just going to be however far this is, okay, which is going to be x1 minus x2, which is going to give me this little bit right here. So that's like saying, I'm going to go to Lauren, I'm going to say, Lauren, here's the deal. All you have to do is I want you to lift 1.2 kilograms up about 10 centimeters. How much gravitational potential energy are you going to store? Oh, and Lauren's going to go, oh, Mr. Burkamp, that's easy. That's just going to be mgh. So it's going to be the 1.2 kilograms times g multiplied by that value. Now, there's a third type of energy involved, and that's going to be kinetic energy. Oh, right, wow, we got kinetic energy. We have kinetic energy because of the fact that when this thing is moving and it's oscillating, right? Now, go old school. Go back to the beginnings of velocity. When this thing is changing direction, and it changes direction a lot, right? So when that thing is changing direction, the velocity has to go to 0. So if you look at this oscillation in slow motion, okay, so if you look at it starting up here, this is when it's going to have its maximum amount of gravitational potential energy, because this is when it's going to be at its highest point. It's going to have its minimal amount of energy stored in the spring, because that's when it's going to be stretched the least. And it's not going to have any kinetic energy because it stopped to change direction. Now, when it gets down to the bottom of that oscillation, my kinetic energy is going to go back to 0 because I have no kinetic energy because it stopped again. My gravitational potential energy is going to be 0 because I'm at the bottom. This is when I'm not going to have any gravitational potential energy because I'm at the bottom. But the energy stored in the spring is going to be at a maximum, okay? Because now I've stretched out the farthest amount. So as that thing oscillates, if you could watch this thing in slow motion, you'd see it start at 0, and then you would see it speed up and gain kinetic energy. But then you're going to lose UG, so UG's going to be decreasing because it's falling. But US is going to be increasing because you're stretching the spring. When you get to the bottom, now I have no kinetic energy because it's stopping to change direction. I have my maximum amount of energy stored in the spring, but I don't have any UG relative to this height because now I'm at my low point. So as this thing is oscillating back and forth, here's the whole point of this. You're going to calculate here on this, you're going to calculate your us at x1 when it's here. How much energy did you store stretched in the spring? You're going to calculate the energy here at x2, and then you're going to calculate the delta us. You're going to figure out how much energy changes in the spring from this point down to this point. Then you're going to calculate the UG, which is going to be mgh. x2 minus x1. So what you should see, theoretically, is that the change in us, okay, the change in the energy stored in the spring here, is going to equal the gravitational energy change when you go from this point to this point. So theoretically, that's what should happen. So delta us, the change in us as it gets stretched, should equal the change in UG from here to here. That's what should happen. So you're going to calculate us1, you're going to calculate us2. Subtract that, find the changes in us. Then you can compare that to your UG value. So what I did 3 trials. So the first one, I had a fairly small, what we call an amplitude, and we'll get into amplitudes later. So I had a small amplitude. On trial number 2, I still used 1.2 kilograms, but on that one, I made the oscillation a lot bigger, okay? So now, with that one, I put more energy into it, so now there's more of a change between x1 and x2 because I made that amplitude a lot bigger, okay? Then on the third trial, I used 1.5 kilograms. So the only thing that happened there is that I swapped that out, I put on 1.5 kilograms, okay? And then I made that 1.5 kilogram mass oscillate, which would be about like this. By the way, you'll get hypnotized and kind of go crazy staring at this, okay? I'm just telling you. So if you're susceptible to being hypnotized, don't go back and watch this. Just, okay. So those are the 3 trials. So if you were actually in my class, this is all the data that you would have. You'd have here to here is x1. This distance has nothing to do with it because this is just the length of the spring. So this is x1, this is x2, this is your height. You'll see that when right away, as soon as we get done, I'm going to scan page 1 so that you'll see exactly where h1 and x2 are. Okay, so let me roll this back over here. Okay. All right, so here's what you're going to do. And I'll send out a scanned image of graph paper in case you need it. So you're going to draw your graph. You're going to put force and elongation. Oh, I hate my camera. Oh! So you're going to have some data points like this, and you're going to come in here and you're going to draw a line of best fit. Now, here's what's going to be most critical. Okay, here's what's going to be most critical. This last elongation is 0.183 meters. So you're going to have your scale, spread out that scale as far as you can. Then you're going to find 0.183 meters, and this is going to be the same for everybody, about 0.183 meters. Then you're going to take a ruler, okay, you're not going to freehand this, and you're going to take a ruler, and you're going to draw that straight up to where it intersects the line of best fit, okay? Not the force that corresponds with it, okay, off of your data. Listen to me. This is going to be the line of best fit intersection. Now, if it happens to be that exact data point that you have for that force, hey, that's great. Odds are it's not going to be. But here's what's going to be. Listen, this is the most critical thing off of this graph. Finding the slope, and for God's sakes, show me that calculation because everybody's numbers are going to be different. Then you're going to come out to 0.183. You're going to draw a line straight up, write down on this graph that coordinate. So this is going to be 0.183 meters, and whatever that value of force is at the point of intersection with the best fit line, okay? I can't emphasize this enough. You're going to come up here, you're going to find this point, you're going to go across, and you're going to find the value of that force, okay? Not the force that corresponds with 1.5 kilograms, but the point that corresponds with the best fit line, okay? Absolutely critical. Because you're going to need that over when you get to, on page, I got everything so screwed up today. So when you get over on page 3, when you get to number 6, it says, using the graph weight versus elongation, determine the area between the line of best fit using the x and y coordinates found on page 1. So what I want is, I want you to find this area, and this is why you had to have the line of best fit, okay? You had to have this point right here. So you're going to find that area. Then on number 7, then you're going to use the equation, so on number 7, you're going to use us equals 1/2 k x squared. You're going to find the energy stored in the spring. This is x. You're going to use the 0.183. Okay? Right? That's going to be the 0.183. So that's cool. Then, on number 9, you want to find the average force. Here's what I want you to do on the average force. You know, it's going to start at 0. You're going to know that final force value up here on that line of intersection. Take the average of these 2 points. Take 0 plus whatever that point is on the line. Divide by 2. That's going to be your average force going across like that. Okay? And then you're going to basically treat it like a rectangle, otherwise known as finding the area of a triangle. Okay, so there's that. So here's what's going to happen the rest of the week. So we're going to do, oddly enough, some more energy stuff tomorrow with what's called elastic collisions. Okay, we're going to do that. On Friday, we're going to have a quiz. Okay, it's not going to be like a full-blown test or anything like that. Okay, it's going to be, I'm guessing, 1 page front to back. Mainly because I don't want us to go all the way through Christmas without having any kind of test over this energy stuff, okay? So on Monday, there's going to be a short test, okay? It won't be anything complicated, it's going to be a short test. Won't be anything like a full-blown like that. There's going to be that. Then, on Tuesday, and this is where I'm open to suggestions. So on Tuesday, I'm not going to do anything directly related to physics. I don't want you all to have any homework going over Christmas break. So some options on Tuesday, we can think of this as just like being an open-ended type thing. So I could talk more about Africa. I could tell more stories about that. That's an option. Okay, that's an option. One suggestion was that I take an hour and kind of explain a simplified version of Einstein's theory of relativity. We could maybe talk about politics. I could just ramble. We could have like an open-ended discussion. You could say, hey, Burkamp, what do you think about this? And we could just have a big classroom discussion. So be thinking about what you want Tuesday to look like, okay? Whether I explain the theory of relativity, whether we talk about quantum mechanics, whether we talk about... Here's one thing we will not talk about is who killed John F. Kennedy, okay? I do know the answer to that question, but I'm not allowed to reveal it. So that's off, that we can't talk about that. But that's a whole other story. Anyway, that I can't tell you all, or I'd have to kill you, and that would just be awkward. It's like, what happened to Burkamp's physics class? Well, I told him who killed Kennedy, and then I had to take him out, and sorry, my bad. Okay, so be thinking about what you want Tuesday to look like. That's it. So go fly, be free, and I will see you all tomorrow.